GPS is famously bad indoors, yet your phone can still put a blue dot near the right place. That is the part people notice first. The useful question is what it tells us about why your phone knows exactly where you are, even indoors, and what the system is actually doing. Night shifters, good evening. I am Night Shift Engineer, checking in from a data center where every blinking light is either routine maintenance or the beginning of a very long night. Let us start simple, then work our way toward the detail the elevator pitch left in the server closet. GPS is famously bad indoors, yet your phone can still put a blue dot near the right shop, gate, room, or street corner. That seems like a magic trick until you notice the phone is not waiting for one perfect answer. It is collecting several imperfect clues, asking which ones agree, and carrying an estimate forward when the sky view gets ugly. The result can feel eerily precise. It can also be wrong by a whole floor, which is the system politely reminding us that an estimate is not a surveillance superpower. Tonight, night shifters, we are opening that little blue dot up, satellites, nearby radios, motion sensors, maps, and the confidence checks that keep a phone from getting completely lost in a concrete building. That is the question for the rest of the episode. Which clue is actually carrying the estimate when the obvious one cannot see the sky? The simple version is sensor fusion. Your phone takes what it can get. Satellite timing when it sees the sky, cellular network context, nearby Wi-Fi observations, motion from its accelerometer and gyroscope, and a map that knows people rarely walk through a solid wall just because a noisy signal suggested it. Not every phone, operating system, app, building, or moment uses all of those inputs. There is no universal tracking machine hiding in every pocket. There are location services that choose the best available estimate while balancing accuracy, power, permissions, and what signals are present. Think less all-seeing eye, more very fast committee meeting with a strict battery budget. The trick is not collecting every signal. It is knowing which signal deserves trust in this particular place, at this particular second. Start outside, where GPS is strongest. Satellites broadcast precise timing information. A receiver compares when each signal was sent with when it arrived, turns the tiny delay into an approximate distance, and combines measurements from several satellites to solve for position and clock error. That is why the system is really about time before it is about maps. A phone does not ask a satellite where it is. It measures how late the signal arrived and solves a geometry problem. Under open sky, that works remarkably well, but those signals are weak by the time they reach the ground. At a roof, a parking garage, or a canyon of glass buildings, and the clean geometry starts arriving with missing pieces and misleading echoes. Once you see GPS as timing geometry, the indoor failure mode stops being mysterious. The clock math simply loses clean inputs. Indoors, GPS does not simply switch off. It becomes a much worse witness. Some signals are blocked. Others reflect from walls, glass, and metal before reaching the receiver. Those reflected paths are called multipath, and they make a signal look as though it traveled farther than it did. The phone may still get enough satellite evidence to help near a window or entrance, but it should trust it less. That is one reason a location service can show a larger accuracy circle instead of pretending its dot is exact. GPS.gov lists indoor use, blockage, and reflected signals among ordinary reasons. Accuracy degrades. The receiver is not lazy. The geometry is badly under-instrumented. A wider circle is not a failure. It is the system declining to invent confidence because the building has opinions. Cellular networks add another clue, usually a broad one. Your phone already talks to nearby cell sites to stay connected, and device or network location services can use cell identity, timing, signal measurements, and known site information to estimate a rough area. People often call this triangulation, but real cellular positioning is not always three neat towers drawing three perfect circles around a phone. The details depend on radio technology, network support, and which measurements are available. The useful mental model is coverage context. A cell site can say, "This device is probably somewhere in this part of the world." That is not enough to find the correct aisle in a store. but it is useful when satellite reception is weak and the rest of the stack needs a sensible starting point. Cellular context is not surgical indoor navigation. It is the broad first clue that keeps the rest of the stack from starting cold. Wi-Fi can be more specific, but the important word is can. A phone can scan nearby access points and observe identifiers and signal strengths. A location service may compare that pattern with a database of where those access points have been observed, or with a building-specific radio map. The pattern is called a fingerprint because it is less about one access point shouting your coordinates and more about the combination of signals around you. Change rooms and the mix changes. NIST has published indoor localization work built around Wi-Fi fingerprints, time series, and floor plan constraints. That does not mean every random router knows your exact chair. It means a familiar radio environment can be a clue if the map is current, the signals are visible, and the location service has permission to use them. A radio fingerprint is a pattern, not a promise. Move the access points, or let the database age, and the pattern needs another reality check. There is a more direct Wi-Fi method too. Round-trip time ranging, often called Wi-Fi RTT. On compatible phones and compatible access points, the device can measure how long a packet takes to make a round trip. Turn that time into a distance estimate and use several access points for multilateration. Android documents 1 to 2 meter results as typical for supported setups. Notice all the caveats packed into that sentence. It needs hardware support, compatible access points, permissions, and an active foreground use case. It still measures a real radio round trip in a world of reflections and busy indoor air. This is not the secret trick behind every indoor blue dot. It is a powerful option when the building was designed to provide it. RTT gets impressive only after you say the requirements out loud. Hardware, infrastructure, permissions, and physics all get a vote. Then there are the sensors inside the phone. Accelerometers measure changes in motion. Gyroscopes measure rotation. Magnetometers can provide a magnetic heading, with the usual warning that elevators, steel, speakers, and the rest of civilization have not agreed to be magnetically tidy. From a known starting point, a device can estimate steps, turns, and motion between radio updates. That is dead reckoning. It is useful because radio measurements do not arrive as a continuous perfect stream, but dead reckoning drifts. A tiny error in step length or heading becomes a bigger error as you walk. Inertial sensing is excellent for carrying an estimate forward for a short time, and terrible as a lone narrator for a long underground adventure. The motion path is useful precisely because it is temporary. A system that knows it drifts has a chance to correct it before the error becomes a confident adventure. This is the fusion step. A location service predicts where the phone should be based on recent motion, compares that prediction with new measurements, and gives more weight to inputs that appear reliable right now. A clean satellite view can matter a lot outdoors. A dense Wi-Fi pattern may matter more inside. A sudden jump that says, "You crossed 3 walls in half a second" deserves suspicion. Some systems use statistical filters, learned models, maps, or combinations of all 3. The exact recipe is product-specific and not a universal public blueprint. The engineering principle is simpler. Do not let one noisy sensor commandeer the whole estimate. In a data center, that is avoiding one bad metric taking over the dashboard. On a phone, it keeps the blue dot from developing teleportation as a hobby. Fusion is where the inputs become a system instead of a pile of sensors. The boring confidence work is what keeps the clever parts honest. Maps add another quiet layer. If a position estimate lands between 2 roads, navigation may prefer the road that matches direction and speed. Indoors, a floor plan can rule out impossible paths and help distinguish a hallway from a solid wall. This is map matching. It does not mean a map secretly overrides reality. It uses known physical constraints to make a noisy measurement more useful. It also explains strange errors. An outdated map can pull an estimate the wrong way. A wrong floor can look plausible when vertical positioning is weak. NIST describes indoor localization as unusually hard, and the vertical axis is especially awkward. Finding the right building is one problem. Finding the right floor through concrete is a separate boss fight. Constraint is not cheating. It is how an estimate uses what we already know about doors, roads, floors, and the inconvenient solidity of walls. So, why is your phone sometimes very wrong? A building may block or reflect the sky. The Wi-Fi environment may have changed. A cell estimate may be broad. Inertial drift may have accumulated. The map may be stale. The operating system may conserve power, lack permission, or decide the evidence does not justify a precise answer. That last one is worth respecting. A broad, honest estimate is better engineering than a fake precise pin. Privacy lives here too. An app only gets the location level the operating system and your permissions allow, and different apps can receive different precision. The practical lesson is not that your phone always knows. It is that your phone maintains a best estimate, with confidence that rises and falls as its clues change. A good location stack would rather tell you somewhere around here than give you a beautiful lie with 6 decimal places. My night shift verdict: your phone does not know where you are because GPS is magic. It knows because location is a layered estimation problem. Satellites provide timing geometry when the sky cooperates. Cellular signals provide context. Wi-Fi can offer recognizable radio patterns, or, in equipped spaces, measured ranges. Motion sensors bridge gaps. Maps keep the result physically plausible, and a good fusion system widens the circle instead of bluffing. The hidden infrastructure is real, but it is not one mysterious machine that never misses. It is sensors, radio maps, permissions, and probability doing their best under lousy indoor physics. Night shifters, which clue surprised you most? The radio fingerprint, the clock math, or the fact that the floor itself is a separate problem? The best part of this design is graceful degradation. When one clue goes dark, the phone still has a way to reason about the next one. So, night shifters, bring it back to the system, not just the surface. Keep the confirmed mechanics, name the trade-offs, and leave room for the unknowns. What part of this system surprised you the most? If you want clear explanations of the systems around us, you know where to find me. Stay caffeinated, stay curious. I need to go tend to an aisle fan making a noise best described as expensive optimism. Night shift engineer out.